As the crossover series continues, we have episode 3 of YBTC and AP Chem. Today we're going to be talking about the periodic table of elements. And for today's video, instead of just yapping a whole bunch and lecturing, I want to show you guys a lot of samples, and I also want to talk a little bit about their properties. Now before we go in, we got to talk about the table itself. So it's laid out like this. So you count left to right, and then you go to the next row once you're done with the previous row. Now here, after barium, you have to go down here. So this is a continuation of row 6. These are the F block elements. They're put down here because if you didn't put them down there, the table would be too long to fit on this paper. Now you can see we have the rows. The rows here mean the number of electron shells an element has. So we talked about it in the last video, but we can see, for example, sodium is on row 3. It has 3 electron shells. Now, just because you have the same number of electron shells doesn't really mean much. In fact, just because an element is on the same row as another element, it means very little. Like, for example, potassium is like a really reactive metal. It can explode when it touches water, or at least catch fire. And on the other side, you have bromine, which is this vicious dark orange liquid which boils easily, and it's going to tear through almost any metal you find. And then there's krypton on the same row, which is like the most innocent gas you could possibly think of. Now the columns here are actually what matters most. So you see the column numbers right here. The reason the columns matter so much more is because the columns, or elements on the same column, have the same valence electron structures. So if you look at the electron configuration video, they're going to have the same portion of their octet completed, at least for this segment right here, the tall segments. They're going to have the same portion of their octet figured, octet done, and because of that, the elements on the same column have similar properties. And the goal of today's video, again, is to just introduce you guys to some of the families, maybe talk a little bit about what they're like. So let's get going. Before we begin, let's talk about the difference between metals and non-metals. So here, let's bring out a few metals here. Let's bring chromium and iron out. Now, some of the defining features of a metal is that, first of all, it's very shiny. So I'm sure we all agree that metals in general are really shiny. This is a piece of chromium right here. You can see just how shiny it is. Another thing about metals is that they're very conductive. So they're good at conducting heat, they're good at conducting electricity. Another defining feature of metals would be that they're malleable and ductile. Malleable means you can bend it without breaking them, and ductile means you can shape it into a wire. To illustrate malleability, you can imagine a paper clip and then bending that. Now let's talk about non-metallic elements. So let's bring out carbon and sulfur as examples. Now you can see here that they're not that shiny. Non-metals in general aren't very shiny. And another feature of non-metals is that they're very bad at conducting electricity. The only common non-metallic material that can conduct electricity is graphite. Every other non-metal doesn't conduct electricity. In addition, non-metals are generally brittle. So to think about it, you can think about bending an iron paperclip, which is a metal, and compare that to trying to bend pencil lead, which is a non-metal. You can see the pencil lead just breaks, but the iron can actually bend easily. And without further ado, let's get to our elemental families. So let's get started with our elemental groups. The first one I have is the alkali metals. The alkali metals are all of group 1 except hydrogen. So lithium, sodium, potassium, and so on. I have sodium right here. And you can see they have one extra electron on top of their normal noble gas configuration, meaning that they're pretty dire to get rid of that extra electron. And as such, they get really reactive. Most, actually all alkali metals have to be stored under mineral oil, like the sodium that I have here, or they have to go under inert gas, because these metals are so reactive that they're going to react with the air or water in the air. However, these metals most form stable compounds after losing their only electron. they form 1+ ions and can form crystalline compounds such as the sodium chloride right here. The next group of metals we're going to talk about is the alkaline earth metals. These metals occupy group 2, and they also have 2 valence electrons. Because they're really close to the noble gas configuration, they're just like the alkali metals and super reactive, although a lot less so. This magnesium right here is stable enough that I don't need to put it in mineral oil. Although for calcium, strontium, and barium, you probably should keep it in mineral oil, and in general, it's just good to keep them under inert gas because they can still oxidize in the air. Once again, alkaline earth metals form 2+ ions to get rid of their electrons, and they form very stable compounds once doing so. Next, we have our transition metals. So the transition metals occupy everything from column 3 to 12 on the periodic table. Now, these guys are actually a very wide and diverse family, including elements like chromium, we have manganese, iron, nickel, copper, and zinc as some of the examples I have. Now these elements seem to obey the periodic trend thing where the same column, similar properties affects them a lot less. But these guys also have very distinct chemistry and very colorful compounds. For example, this right here is a bluish compound that forms when chromium loses 2 electrons. Let me try and zoom in here. So when chromium loses 2 electrons, it forms this nice bluish color. It's wrapped in the plastic wrap and stored under oil to prevent it from oxidizing. Similarly, manganese forms these nice pinkish color crystals after losing 2 electrons. However, it can also form purple, green, brown, or blue based on the different numbers of electrons it can lose. A main defining feature of these elements is that they form colorful compounds like these, but they also form multiple different oxidation states. In fact, pretty much everyone here except zinc can form more than one different oxidation state. Now we go on to the rare earth metals and lanthanides. The lanthanides aren't actually covered that much in the AAP, but it is in the YBTC guides, and it's just fun to learn about more elements. So here I have europium, gadolinium, terbium, and holmium for samples. These lanthanide elements are very similar to each other chemically. They're all somewhat reactive. Europium is especially reactive. I put it in mineral oil because it's just that reactive. They almost always form 3+ ions, but because of the unique atomic and electronic structures, they form various very important technologies. In fact, the screen you're watching this on right now probably has europium and terbium at the very minimum, so that you can see RGB colors. The next group we'll go over is the halogens. I don't have any samples, but I can show you a salt of one of them. This is sodium chloride, which is a salt of chlorine, and it illustrates really well the behavior of halogens. If you look at the periodic table, the halogens are right next to the noble gases, and because of that, they're really desperate for that extra electron to satisfy their octet. And it forms compounds like these, gaining an electron from other metals so they can satisfy their octet. Other members include fluorine, bromine, and iodine. Finally, group 18, the noble gases. So noble gases already have a stable electron configuration, and they don't tend to react with anything. So helium, neon, argon, and others are part of the noble gases. Here I have an ampule of krypton from Mr. Anwar. So these gases don't really want to react. The molecules don't really bind too tight to each other either. So here I have it in an ampule. It does make really cool trails when you put it in a Tesla coil. So that was the periodic table. Thanks for watching. See you guys next episode.